In the last week, we were introduced to unitary matrices, orthonormal matrices, and the singular value decomposition. And by the end of the week, we still actually didn't have an algorithm with which to compute the singular value decomposition. And the fundamental problem there is that it's very hard to compute. Still, we want to be able to identify orthonormal matrices, orthonormal bases for the space that we're trying to describe. In this week, we're going to start in this introduction by discussing a problem that illustrates how important it is to choose your bases correctly. And then we move on to practical algorithms for computing such bases. So let's have a look at that. All right, a classic problem that you've probably seen before is the problem of approximating a bunch of points in two-dimensional space with a function that goes through it. So you've gathered some data, you know that data is a bit noisy, you would like to find the function that does a good job of approximating it, and often you do that by saying, well, we're going to approximate it with a polynomial. So this is gamma 0 plus gamma 1 times chi and so forth. So this is a polynomial in chi. And we would like to compute this approximation. I should have used chi right there for x as well, because we like to use Greek lowercase letters for our scalars. All right, so if we could exactly put the polynomial through all of these points, then if we plug in chi 0 into the polynomial, we should get psi 0. Sorry, that's phi 0, the Greek letter phi. If we plug in chi 1, we should get phi 1, and so forth. But generally speaking, especially if m is greater than n, we can only approximately satisfy this, and then we get the problem of trying to find these coefficients gamma 0 through gamma n minus 1, such that we satisfy this approximation. And how to find the best coefficients is actually a topic for week 4. In this launch, what we want to do is look at the matrix that comes out of this, and we want to discuss its condition number. How could we do that? Well, notice that we, instead of writing this as a set of linear equations, simultaneous linear equations, we could instead write this as the following matrix. See, these are the columns of the matrix. The first column is all ones because it's really chi 0 to the 0th power, chi 1 to the 0th power, and so forth. So here we have the matrix, which must multiply gamma 0, gamma 1, and so forth through gamma n minus 1, and that should be equal to phi 0, phi 1 through phi n minus 1. Okay? But again, typically we don't expect this to be exactly satisfiable, so we'll put an approximate in there. And this is the matrix with which we're going to concern ourselves. Okay? It has a special name. It's known as the Vandermonde matrix. Now, one way of thinking about this is that what you're really trying to do is approximate the function by taking linear combinations of the parent functions. Okay. What are the parent functions? Well, the first one is just the polynomial y equals 1. And then the second one is this polynomial, and then the third one is this one. In other words, these are the parent functions that show up as the terms or the functions with which you're trying to take linear combinations to approximate the function. And you can kind of look at this and see that this is going to be trouble, because as you go to higher and higher degrees x to the kth power, these functions here start looking very similar, and therefore taking linear combinations of those functions, picking out just the right one becomes difficult. And what happens there is that translates into these columns here becoming approximately linearly dependent. And if the matrix has columns that are approximately linearly dependent, then that translates into a condition number that is very large. Okay. So in a homework, what you're going to do is program up the computation of this matrix, and then you're going to use the function COND, which returns the condition number for the 2 norm for a matrix when you enter it. And with that, you're going to examine what happens to the condition number of this matrix as n gets large, and you're going to find out that that condition number gets very bad. Now, strictly speaking, you don't yet know what the condition number of a rectangular matrix is, but we'll get to that topic in week 4 as well.